Today I'll talk a bit more about linear transformations and kind of in more generality, but I'll maintain a focus on matrices. So a linear transformation is simply a function from Rn to Rm, where n and m are natural numbers. So it could be from R2 to R2 like we saw last time, but it doesn't necessarily need to be. So if that transformation has these properties, then we call it a linear transformation. And these are the two defining characteristics right here. One is that if I take the transformation applied to the sum of two vectors, then it's just the sum of the transformation applied to the individual vectors. The other one is if I multiply a vector by a scalar and then apply the transformation, it's the same thing as if I apply the transformation to the vector first and then multiply it by the scalar. Okay? And we isolate these as kind of a special class of functions worth studying because they pop up in so many different settings. So here's an example here. G of x is just equal to negative 4 times x. So this is a function. It goes from the real numbers, takes real numbers, and then it maps it to real numbers. Okay? And if I took any two real numbers, let's say x1 and x2 are real numbers, this just means are in the set of real numbers. Then if I take g and I apply g to the sum of x1 and x2, well, that's just going to be negative 4 times x1 plus x2. I just sub that in for the variable. Okay. And I can distribute that negative 4, so I have negative 4x1 plus minus 4x2. Okay. And if you look, that's what I would have gotten if I would have applied g to x1 and added what I would get if I applied g to x2. Okay? So that's that first property of linear transformation. If I apply the function to the sum of two vectors, in this case real numbers, then I get the same thing as if I applied the transformation to each of those vectors individually. Okay. This also has the second property. So if I took some element of the real numbers and then I subbed it in there, or I multiplied it by any sort of constant, then I would just have negative 4 times that constant times x. I just sub that in. And I could use the commutativity of multiplication and do this. Maybe I'll write it like that, put an x there. And that's the same thing as if I multiplied by the constant after I applied the function to that element of the domain. Okay, so it's a bit of a simple example, but it illustrates what it means to be a linear transformation. It has to have these two properties. Okay, you can see that that's probably also going to hold for the second example, something worth checking out. But now if I did the same thing here, so for example, if I took two elements of the domain, so x1 and x2 in the real numbers, then if I tried to sub them into h, like this, I'm going to get this. And you can check if you expand that those brackets here, that exponent. I'd have x1 squared plus 2x1 x2 plus x2 squared, and so on. And if you compare this to what you would get if you applied h to both x1 and x2 individually, you would have this extra term in there. So this definitely does not equal h of x1 plus h of x2. Okay? So in this case, in this third case, that first condition is violated, so it ends up not being a linear transformation. Okay? And you can check, you should check, that multiplication by a matrix is also a linear transformation. Okay? And that's what I put here as a bit of a summary. Okay, so what we've seen in the last video is that when we have a square matrix, we're mapping from, in our example, R2 to R2. In general, if I have an n by n matrix, then that matrix multiplication is mapping Rn to Rn. And so we don't really need to have a square matrix in order to think of matrix multiplication as a linear transformation. Okay, I could have these other examples, and you can think about if these are used as in multiplication, where would they be mapping from and to? Okay, we could take, for example, this. We have one row and two columns. So what would the matrix look like over here, and what would it end up being in that multiplication? Okay, so think those through, and those are something we can talk about when we're in person. One particular case of that is that sometimes when I multiply by a matrix, I kind of collapse the dimensions. I make the space smaller. Okay, what I mean by that, let's look at what happens when I multiply this matrix by this vector. So I've got 2, 3, minus 3, so that gives me 0. Then I have 0, 3 minus 3, and then minus 4, minus 3, plus 3. This goes to 0. So what happened here, I have a non-zero vector suddenly being mapped to the 0 vector, so it's kind of collapsing that three-dimensional space along that vector. It's reducing the dimensions. Here I had something that's non-zero, but I end up going to something that is 0. This is an example of vectors in a null space of a matrix. Okay? What it is that if I look at all vectors that have this property that get mapped to the 0 vector, I call that the null space of the matrix. Okay? Now you can suspect that this doesn't always happen. Sometimes that null space is just the 0 vector. It doesn't have any non-zero vectors in it. Okay? But in particular cases, in here, for example, we do have that non-zero null space, all vectors that get mapped to the 0 vector. Okay, so this null space, we're going to talk more and more about it, and something called the column space. These are all examples of linear spaces associated with a matrix. Okay, now a linear space, this is already a familiar concept. Perhaps you haven't applied that name to it, but it's the spaces that you're most familiar with in mathematics. For example, R2, the plane, R3, right? It's the space we live in. These are linear spaces, but they're not the only examples. We could think of subspaces of a linear space. Okay, so spaces within a space, and see if they're linear or not. Okay. In this case, one of the most familiar examples is a line through the origin in R2. It's a linear space. And we could think of about a plane in R3 going through the origin. That's also a linear space. So we're going to talk more about linear spaces next time, and we're going to look at different linear spaces associated with a matrix.